Hello everyone. As mentioned, I want to talk about decidability in Borel monadic logic, and in particular about the Borel monadic theory of order of the real numbers. So I will start by first introducing or reminding all of you what monadic logic actually is, and somehow getting to the context of the question and why it is interesting. Then I will also talk a bit about the specific technical setting with restricted monadic quantification. I will try to talk a bit about the proof, and finally I would like to mention some related questions on the Borel monadic theory of the infinite binary tree. Okay, so first of all, what is monadic second order logic? Well, in first order logic, we quantify over elements of the given structure or universe. Quite powerful expansion is second order logic, which allows not only to quantify over elements, but over arbitrary, possibly n-ary relations on the universe. And monadic logic is intermediate between those two things. In monadic second order logic, we can quantify over unary relations of the universe, but not over relations on Cartesian powers. One reason we restrict to, in model theory usually we restrict to first order logic, and most good properties of first order logic like compactness and Löwenheim's golem and so on fail for monadic logic. And also if we try to get decidability, there are strong limitations in higher order logic. Let's for example look at the natural numbers. In first order logic, it's quite well known that if we take the theories of the successor function of order, the Pressburger theory arithmetic, the theory of addition, or full arithmetic, we get increasingly more powerful theories, and all up to including Pressburger arithmetic, labeled green here, is decidable. If we go to full second order logic, on the other hand, it's quite hopeless. Even if we only allow the successor function, one can mimic the usual definitions, or express the usual definitions of recursive definitions of addition and multiplication using, and thus obtains that this actually is the same as the theory, second order theory of full arithmetic, and thus clearly undecidable. In monadic logic, everything is a bit nicer. While addition still is not tractable because it allows one to recover multiplication, if we restrict to order, we get actually a decidable theory. And actually it also turns out that in this result, restricting to order or the successor function is equivalent because order can be defined by having by the existence of a subset in between, which is a chain with respect to the successor function. Okay, so we have seen that we cannot really talk about algebraic structures on the of monadic logic. Also, for example, the theory of the rational numbers with addition or the real numbers with addition and monadic quantification easily leads to undecidability. So when we look at monadic logic, we really should focus on theories of order if we want to get tame theories. Let me also mention shortly something else here. If we pass to second order arithmetic, which is the same as which is also expressed by monadic arithmetic, we get also something more powerful than first order arithmetic, the definable, which talks about somehow real numbers, and the definable sets are called the projective sets, which will also reappear later for some other perspective. Okay. So that's about order. So why is the monadic theory of order, as I mentioned, decidable? The classical proof of Büchi goes using so-called omega automata on infinite words. They are not what I use for the results of this talk, but they will appear shortly towards the end of the talk, so maybe let me shortly give you an example of how they look and what they can do. And let me just write down an automaton for the monadic formula which expresses that x is a finite subset of the natural numbers. and use this example to explain roughly how those automata work. So such an automaton has a finite number of states. In my case here, I will use 3 states. One of those states is the initial states, and those states have transitions. The idea is that the automaton will read this set regarded as as an infinite 0-1 string. 1 means that the nth element is in the set, and 0 means that it isn't, and then decide somehow whether it accepts. So we add some transitions here, which say that if it reads this digit, it may transition to another state. For example, this state here means that it still is in that its initial segment it wants to leave, so it can stay here by reading zeros or ones. At some point it will say, okay, the set is finite, now I have decided that I reached the end of the set, and then it can move to the second state, which will be marked as a particular accepting state, and which can be reached with zeros. However, while it can remain in this accepting state only when it keeps its promise that it won't see any further ones anymore. And finally, if it still sees a 1, then it somehow has failed and enters this failed state. And then the automaton accepts the input string if and only if it manages, by choosing its transitions correctly, to ultimately remain in this state. Okay. So those automata can be used to describe any monadic formula, and the operations of them can be computed efficiently, and that is a way to obtain decidability for the theory of the natural numbers, or also for some more expressive theories. However, there's also an alternative. So, for example, using an analogous result for infinite trees, one can deduce decidability of the monadic theory of the rational numbers with order. And actually, there's also another more algebraic proof, which will be more similar to the things I will discuss later in this talk, of the decidability of the monadic theory of the rational numbers with order. Also note that the monadic theory of the rationals is really the same as the common monadic theory of all countable orders, because we can quantify over subsets, and every countable order embeds into the rationals. However, those decidability, here we really reach somewhat surprising limitations of decidability at the rational numbers. Namely, if we pass to the monadic theory of the real numbers, then it was proven by Gurevich and Shelah that we get an undecidable theory. And yeah, it's really about the uncountability here. Somehow, if we take other related theories, say the Cantor set with the lexicographic order or something like this, we also get undecidability. Maybe, while in the first order setting, of course, the reals and the rationals have the same theory, but in the monadic setting, this is no longer the case. For example, we can have a monadic formula which expresses that the underlying order is a Dedekind complete order. And which we need to take into account if we want to consider the theory of the real numbers. Well, and of course the rational numbers do not satisfy this theory. So this, if you check the definition of being Dedekind complete, you really can phrase it in a monadic setting. Okay, and it also turns out that the theory is related to the theory of topology. I will say a bit more about this later. So what's the idea of the undecidability proof? Oh, that's not good. Great. The idea of the undecidability proof is that using some very complicated parameter sets, which need to be defined by transfinite recursion, we can encode quite complicated relations into simple relations between Cantor subsets of the reals. Actually, there is a precise set-theoretic way to phrase this, namely this theory can express third-order arithmetic, but not in the ambient model of set theory, but in the forcing extension of this model of set theory obtained by adding a single Cohen wheel, which somehow corresponds to the regular open subset of the wheels, which play a role here. And so this very complicated parameter set crucially depends on the axiom of choice and on some very undefinable sets. It actually turns out that if we restrict quantifications, we can get decidability, and this is what I mainly want to talk about today. Namely, that the main result here is that the Borel monadic theory of the wheels, so if we restrict the monadic quantifier to Borel subsets of the wheels, is a decidable theory. Okay. So it was known before using the tree automata of Rabin that the F sigma monadic theory of the wheels, where the F sigma sets, which are countable unions of closed sets, are the second level of the Borel hierarchy, yield a decidable theory. And in some sense, this was already quite close to what the Borel monadic theory is. Namely, it turns out that the Borel monadic theory is the same as the monadic theory for Boolean combinations of F sigma sets. So just a tiny bit further. And then this is also quite a stable phenomenon. So if we go to, for example, some intermediate level of the Borel hierarchy, then we also get a decidable theory. While undecidability can happen quite shortly above the Borel sets, because, for example, it's at the projective sets, which I mentioned, because it is consistent with ZFC that there is a projective well-ordering of the wheels, which would allow to carry out Shelah's undecidability proof in this setting. It turns out that it is also, under nice situations, we still get decidability for those larger classes of definable subsets of the wheels. For example, if we are willing to assume projective determinacy, which holds assuming some large cardinals, then we get that the projective monadic theory of order is also definable. Interesting contrast to Shelah's undecidability result, which used the axiom of choice, if we are willing to drop the axiom of choice and replace it by the axiom of full determinacy, which somehow states that all sets of wheels are well behaved and like definable sets, then we can really get decidability of the full monadic theory of the wheels. And it's also the same as the Borel monadic theory in this case.
What is DC?
Oh, it's the restriction of the axiom of choice, the axiom of dependent choices, which is also needed for my proofs. And which is the relevant point here is that this restriction of the axiom of choice is still compatible with the axiom of determinacy, while the full axiom of choice is not. Yes?
So in the previous slide, there was a theorem that the monadic second-order theory of the order on the reals is undecidable, so that was proven using full choice?
Yes, this needed full choice because there is this very complicated parameter set which depends on a well-ordering of the wheels, essentially. Okay. So, yeah. Let me also shortly mention the relation to the monadic theory of topology. We can replace order in the language by a predicate for open subsets. So then we equivalently only get the first order theory of the sets we quantify over, like the Borel sets, together with the Boolean algebra structure, which can be defined, saying the inclusion relation, and a predicate for being an open subset. This still allows to express many classical topological properties, like being, say, connected. And is essentially the same as the monadic theory of order. Well, we can clearly define topology, the order topology, on using monadic logic, because the definition just depends on intervals of the wheels. But we can also conversely recover the theory of the theory of order essentially from the theory of topology. We do not quite literally get full order back because, of course, flipping the order on a line is an autohomeomorphism, which is not an order isomorphism, but we can at least define the relation that y lies between x or z in the theory of topology, and this essentially is as good as order for decidability purposes. So this relation that y lies between x and z is equivalent to the statement that for all connected sets I, if x lies in I and z lies in I, then we also have that y lies in I. Okay. Yeah. Using this definition of topology, this result will also imply that the theory of topology of the class of zero-dimensional Polish spaces is decidable, but let me also mention that some restrictions on the dimension here really are necessary, because if we go to R2 or so, then we can easily express classical geometric notions in those Borel monad theories of topology, or also theories with much smaller classes of sets we quantify over, and using this easily interpret arithmetic in those theories. Okay. So yeah, let me finally expand a bit on my discussion on the class of sets we could apply all of this to. The proof, the decidability proof really requires only determinacy and some technical closure properties, like that allow to reconstruct the labeling of the reals from reconstruct the subset of the reals from its restriction to a Cantor set and the intervals which form the complement of this Cantor set. In some way I don't want to make precise here. And actually it's not clear how much determinacy really is needed. So the main technical property we use is the Baer property, which is an equivalence of Lebesgue measurability for meager sets instead of Lebesgue null sets. Which is a consequence of the axiom of determinacy, and in particular, but also holds, for example, for the Borel sets for the same reason. But in one situation, the proof uses a gain beyond this, and it's not clear whether this can be eliminated. And for example, there are also natural classes of sets which satisfy the Baer property, but not full determinacy. For example, say Boolean or sigma combinations of analytic sets under the axiom of constructibility. And in this case, I currently don't know whether the theory is decidable. Of course, if we go further up in the projective hierarchy, as I mentioned, we can get undecidability. Okay, so much about the context. So next I would like to say a few words about the proof, which builds on a technique developed by Shelah when he tried to prove decidability of the full monadic theory of the reals before establishing undecidability. And because some notation here will be much more convenient, so let me just introduce it here. Of course, monadic logic quantifies over subsets, but it's usually nicer to restrict to subsets which form a partition of the given of the universe, which can of course be assumed. And so this could be equivalently phrased as a map called a labeling towards a finite set, or if you use automata theoretic language, alphabet sigma. Yeah. In model theory, we usually study types, or if we want to do decidability, only finite partial types in some sense. And here, so types are theory, you can be thought of as theories with an added constant symbol for elements or tuples of elements. And similarly, here we would add an somehow added symbol, but not for first order constant, but for monadic constants or equivalently labelings. And then instead of quantifying over additional subsets, one could just quantify over a refinement of the given labeling. So a labeling by a larger set through which the old labeling factors. And yeah, whenever I will speak about something like embeddings or isomorphisms or something like this between such labeled orders, I really talk about maps which preserve the order and preserve the given labeling. So they will have the same sets of labels. Okay, so and now with this notational context, we can talk about Shelah's decidability technique. which is somehow a bidirectional analog of automata. When automaton would only pass from left to right towards an order, this will need to be able to pass through the order into both the left and the right direction. And it's a generalization of some methods with monoids for finite worlds. So, yeah. But to even phrase these results, we need to first restrict to particular subsets of the theories. So we do induction on a generalized quantifier prefix, k, where somehow the length of the tuple should denote the number of quantifier alternations, but the size of the individual quantifier blocks does also matter and is encoded by the components of the tuple. So we will do induction on a number of quantifier alternations, but generally in our inductions the size of the individual quantifier blocks may increase. Yeah. And this can also be made formal by we start with considering atomic formulas. In each step we take first Boolean combinations of all formulas we have before and then allow a layer of say kn additional quantifiers. Okay, and then we will use this notation thk to denote all those formulas up to quantifier when k, which are satisfied by our model x together with a labeling p. And yeah, the point really is because we are in a relational language, there are only finitely many atomic formulas, and so each thk, at least up to logical equivalence, is a finite, up to trivial logical equivalent, propositional logical equivalence is a finite set. And so really what we need to do if we want to prove decidability of the reals is to compute the map which sends a quantifier prefix k to the k theory of the real numbers. And the point in using this somehow weird stratification of all formulas is this compositionality result of Shelah, which says that if we have a total order and the summands and take a lexicographic sum with summands also label total orders, then the theory of the lexicographic sum, so the disjoint union of the xi, where the different xi's are compared as by the order given by I, is determined by the theory of I with the if we label each index by the restricted theory of its summand. We will use this in different settings, for example, for binary sums, where it really just says that the sum of two elements of two orders is determined by the theories of the summands, but also for infinite sums and also for decomposing the real numbers somehow into a Cantor set at its complementary intervals. By the way, this is somehow analogous to the Pfefferman-Ward theorem in model theory, which says that you can recover the theory of a Cartesian product from the theory of its factor.
So you mean there is a k prime such that every k there is a k prime?
Yes, for every k there's a k prime which we can compute from k such that this holds. Okay, so the next point of Shelah, which allows to decide the rationals by this other technique, is to investigate somehow uniform labelings. So the idea is that a labeling is uniform if it looks the same on every open interval, and looks the same needs to be phrased here in terms of those restricted theories. So for example, if you look at a countable subset of the reals, then uniformity guarantees that it's either empty or dense. And this is essentially everything you need to know about this countable set. Moreover, this condition to look the same on every open interval, it turns out by this lexicographic compositionality argument from the last slide that it suffices to check this if you restrict the endpoints to a given dense subset of the reals, say the rationals. And this is really helpful because it allows us to use some Ramsey theoretic result of Shelah here. Namely, by Ramsey theory, since we have somehow only those finitely many types, we can show that, and using previous result, we can show that every labeling is uniform on some open subinterval of its domain of definition. And then if we take all those open subintervals inside open sets and repeat this procedure, we somehow arrive at an open dense set which we somehow control. And the complement, after handling the isolated points and so in a relatively straightforward manner, is seen to be really a Cantor set, which somehow explains the connection of the theory of the real numbers with its sub-Cantor sets. And so really Shelah managed to reduce arbitrary monadic quantifiers over the reals to just quantifying over somehow uniform labelings and uniform refinements thereof, at the cost of also introducing those new quantifiers over Cantor sets. And those Cantor sets themselves, of course, will never be uniform in the above sense because they are closed sets, but we can assume that the labeling restricted to this Cantor set looks somehow uniform to this Cantor set itself again. Yes. And in the case, this also works in the non-Borel case, and here we really get undecidability because still those uniform Cantor sets are impossible to control. But the difference here is now that we can control in the Borel setting the uniform Cantor sets using bare category methods. So as I mentioned, it remains to understand those two types of quantifiers. The combinatorially more interesting type of quantifiers, I would say, is the quantifier over the additional Cantor sets. And first of all, in the Borel setting, we know that many Cantor subsets of the reals exist. For example, there is this perfect set property, which states that every uncountable Borel subset of the reals includes a Cantor set. But we also can say when they do not exist, namely it turns out that if a type of a Cantor subset which could be realized a priori is not realized, then there is a bare category reason for this, and the decidability proof just needs to understand those bare category reasons. However, passing to the general quantifiers of a uniform refinement is where currently this determinacy argument is needed to somehow separate everything nicely into F sigma sets. I should also shortly mention that in some previous version I claimed that this would not, I didn't claim that this would be necessary and that we would get decidability for analytic sets, but I needed to fix some error here, and since then this additional determinacy argument became necessary. Okay. So how do these bare category arguments look like? Let's look at a simple example which I think is nice because it captures some of the main ideas of those bare category arguments, namely the definition of the meager set, of the class of meager sets in the Borel monadic theory of order. So the point of this long equivalent definition of meagerness is that it is easily expressible in the Borel monadic theory of order. And so let me just try to prove this characterization of meager sets for you now. Okay, so let's first look at this implication. If for all non-empty open subsets U there is a dense Borel subset B such that there is no Cantor subset C inside A union B, such that B is dense in C, that then A is meager. So let's assume that A is not meager. Then by the bare property, which we know that A is co-meager in some non-empty open subset U. So let U be non-empty open such that A is relatively co-meager in U. Okay, so now we have chosen our set U, and now this claim gives us that we obtain a set, that we obtain a dense subset B. And now we just need to obtain a contradiction, so we need to construct a Cantor subset, which is a subset of A union B, such that B is dense in C. So we need to somehow first avoid a small, meager set inside Cantor sets. This is generally easy to do in descriptive set theory because, for example, the remaining set is still a G delta set, so a Polish space, and contains a Cantor set. But we also still need to make sure that B is dense in here. That's not too problematic to do, but I don't want to do the technical details of this part here now. The other direction is more interesting because it contains the bare category arguments we are actually interested in, and luckily I can also give a complete proof here. So now assume that A is meager because this property, because the right-hand side is monotone in A, as you can check, and every meager set is included in a meager F sigma set. We can assume that A is a union of closed sets as AN, and then automatically those closed sets need to have empty interior because A is meager. Okay, and now we need to choose this. Now we are given this set U, which is open, and we need to choose a dense set B, and actually it suffices to take a countable dense subset of U without A. And of course we can take such a countable dense subset because our set B, because U is an open set and A is a meager set. Okay. And now we are given this Cantor subset C, which is a subset of A union B. And then, so B is countable, and those AN are also countably many summons. So B is included in this countable union. So one of those countably many parts needs to be non-meager in C, relatively non-meager. And of course, the countable set cannot be. So sum AN is non-meager in B. So in C. This implies, because AN is closed, that AN has non-empty interior. And so we have seen that A has non-empty interior, but A is disjoint from B. So this means that B is not dense, and we have obtained our contradiction. Okay. So in some sense, this is only an elementary point set topology argument, but the later bare category arguments in some sense resemble this argument. Okay, so now that we have discussed this here, let's talk shortly about how to push this up to the general case. So by the results of Shelah, which I mentioned allowed us to reduce to this particular kinds of quantifiers over uniform sets and over Cantor subsets, we also know that every partial type can be built using uniform types, using additionally binary lexicographic sums and infinite sums with index at the naturals or minus the naturals. Okay. So it turns out that to obtain all possible Borel uniform types, we really only need one additional operation, which I called the uniform sum, and where the idea is to somehow shuffle Cantor sets in such a way that we obtain dense many copies of them and thus obtain a uniform subset in the end. So more formally, we are given as input some labeling of the Cantor set, which we want to shuffle throughout the reals, and some, sorry, I don't, yeah. Okay, I think this Q shouldn't be there, sorry for that. and we get some individual label for the remaining part. So, and the idea is we start by embedding this Cantor set, which is labeled by P, into the reals. So what we get is then this part Cantor set, which we understand, and all those countably many complementary intervals, which we still need to label. And into each of those complementary intervals, we recursively again embed this Cantor subset. And then we iterate this procedure. At each step, we still only have a Cantor subset. But in the limit, if we stop this after omega steps, we will get a countable dense union of Cantor subsets. And we will have this remaining points, which we don't have labeled yet. And we might label all those remaining points uniformly by this individual label sigma naught. Of course, that this can give something that completeness crucially depends on the Baire property, because, well, those countably many counter sets will still be a meager subset of the reals. So we will have taken an entire co-meager part of the reals and declared that we labeled by sigma naught. But, well, because Borel sets have the Baire property, we can't really hope for something else to happen. And it turns out that this operation is complete in some sense. Okay. So this is how we obtain all types of the reals, but this, so far, I only talked about some real understanding how Cantor sets embed. So yeah, sorry. Yeah. And now using those things, we can really realize all possible ways how Cantor sets embed into each other, namely for a Borel labeling. By this Baire property, as I mentioned, every label is either meager or co-meager. There's this unique co-meager label, which by uniformity really needs to be there. And so the question we need to answer for this type of quantifier of Cantor sets really is if we have a labeling of the Cantor set and a labeling of the reals, does this copy of the Cantor set embed into this copy of the reals from somehow the type of both? And if the two have the same co-meager label, then in all reasonable circumstances we can embed them, because this large co-meager set gives us very much wiggle room to combine small Cantor sets. This is essentially the same thing as we did in the step here, where I mentioned that it's easy to construct this Cantor set now because we have this co-meager set A. Yeah, if they do not have the same co-meager label, then again this Baire category obstruction as in the other direction of the proof may occur and block us from realizing this type. But again, those Baire category obstructions can be understood quite explicitly. So in some sense they make the question whether Cantor sets with different co-meager labels are realized independent of each other for different Cantor sets. Okay. So, so far I have talked about how to control embeddings of Cantor sets, but there is this second part type of quantifiers which we do need to understand for Shelah's result, which is the quantifiers over uniform refinements. And here it turns out to be helpful to separate the reals into nice F sigma sets, which again can be controlled independently for the question of refinement. So let me mention a result of Hurewicz, which actually allows to define being F sigma in the Borel monadic theory of order. Namely, a Borel subset of the reals is F sigma if and only if it somehow is not obviously not F sigma in a Cantor set C, and a way to be obviously not F sigma is by being a non-trivial co-meager G delta subset somehow. And so yeah, we demand that this formally holds F. By the way, this definition of being an F sigma set inside the reals also allows us to give another definition of meager sets, which doesn't use this Baire category argument, because a subset is meager if and only if it is included in a meager F sigma set with empty interior. But nonetheless, I think that this argument over there is nice, and in contrast to the Hurewicz argument, it also doesn't depend on any determinacy or so. Yeah. And so it turns out that the uniform refinements, as I mentioned, are controlled by partitions into Boolean combinatorial sigma sets, which can be independently refined, and this is where I used the determinacy argument. So I don't want to go over this in detail, but so this is only second kind of game I use beyond implicitly the game for the Bear property, which would be a Banach-Mazur game. So in the Banach-Mazur game, one player somehow tries to prove that that a given input set is co-meager in some non-empty open subset, while the other player tries to prove that the given input set is meager. And similarly, for my separation games, given a labeling, one player called separator tries to prove that it nicely decomposes into simpler labeling, say using less labels, on simple subsets, say intersections of a sigma and G delta sets, while the other player, here called Pathfinder, tries to deduce that there is a Cantor set in which everything behaves in a very complicated way. And yeah, formally the idea would be, so they need to alternately create some data, and so Pathfinder would try to build up a wheel over the course of the play, so he would just play the digits of the wheels, while Separator would play the numbers would play some of the possible numbers which roughly correspond to labels, and which allowed Separator to label the given real numbers in some continuous way. And then one can use the limit superior of this infinite sequence. The more numbers Separator can choose, the more freedom they have to split things into sets as they wish, and thus to win the game where they ultimately try to avoid a certain given label. But, yeah. Given the time, I won't talk about the technical details of this game much, and instead finally talk about some related conjecture of Shelah about the Borel monadic theory of the binary tree. So when Shelah conjectured the decidability of the Borel monadic theory, he also conjectured the theory of the Borel monadic theory of the binary tree, where you would have the infinite binary tree and can quantify over sets of nodes or over Borel sets of branches. So if you only can quantify over Borel sets of branches with the lexicographic order, this is just the Cantor set with the lexicographic order, so essentially the same thing as the reals and precisely what the current decidability proof is about. On the other hand, if you only restrict to the nodes, then you recover the tree automata of Rabin and the monadic theory of two successors. And so the hope is to have this nice common upper bound of those two theories and still obtain a decidable theory. And really this new common upper bound also expresses things that the individual parts do not. For example, if you think about determinacy of a game, this really can be expressed in this language. So this theory knows that Borel determinacy is true, that every game with a Borel payoff set is determined by a single sentence. And so we cannot hope to only prove decidability by some bare category method and maybe some single limited topological game as we did here, but really need to consider arbitrary games if we want to understand this theory. But nonetheless, it might be true that we can find an analog of Rabin's tree automata, which still works on those infinite trees, and this is what Mikołaj Bojańczyk, Antonio Casares, and Paweł Paweł and me are trying to do in ongoing work. But let me shortly mention the main idea by remembering how the tree automata of Rabin work. So the key of the proof for Rabin's tree automata would be that the sets which are recognized by such tree automata are stable under complementation, so that we can really obtain a logical theory. Maybe let me shortly mention what such a tree automaton is. I shortly introduced those automata for infinite words, which will have a single pass over the word, and at the end may make some choices non-deterministically, at the end have to decide whether they accept or do not. Tree automata now get an entire tree as input, so they have somehow to and need to pass it somehow. And one nice way to express this is that the movement in the tree is specified by a game that is played between the automaton and a pathfinder, which tries to find a path in the tree. This play then will lead an infinite branch on which this automaton roughly behaves like a usual automaton in infinite words. And so then actually complementation can be achieved by roughly quantifying over strategies of your opponent. And to do this, which is also how S2S is proved in modern accounts, like the one of Gurevich and Harrington found to simplify Rabin's proof. And there really the combinatorial key property is some kind of finite memory determinacy. Not only those games that are played between automaton and pathfinder are determined, but they can be won using only a finite amount of memory over which an automaton can quantify. And so we hope that there's still some appropriate, or we have a conjectured finite memory result for general Borel games, which would apply that our automata model would work for this. Of course, finite memory needs to be somewhat restricted here, actually already even in the case of tree automata, because the input of the tree, which in our case could even be arbitrary Borel sets, also can be taken into account without using parts of this memory up. Okay, but that's also anything I had to say on the theory of the infinite binary tree, so thank you for your attention. Are there any questions?